Welcome to G Fun Facts Online. Today we are dismantling the engine of the 20th century and rebuilding it from the molecule up. For over 100 years, the history of human flight has been written in the language of crude oil. The roaring engines that shrank our world were fueled by the decayed remnants of ancient marine life, refined into kerosene. This dense, energy-rich liquid powered the globalization of commerce and culture, but it came with a heavy cost. A massive pulse of carbon dioxide and particulate matter injected directly into the sensitive upper atmosphere. As aviation enters the late 2020s, a fundamental chemical shift is underway. We are moving from extracting carbon from the geosphere to recycling carbon from the biosphere and atmosphere. This is the era of Sustainable Aviation Fuel, or SAF. This is not merely a change in supply chain, it is a revolution in chemical engineering. The transition to green flight requires mastering the molecular architecture of hydrocarbons, designing catalysts that can reconstruct jet fuel from algae, waste grease, and even thin air. Today we are exploring the deep chemistry of SAF, detailing the reaction mechanisms, catalytic pathways, and thermodynamic realities that define the future of aerospace propulsion. To understand the chemistry of green flight, one must first understand the chemistry of conventional flight. Jet A1, the global standard for aviation turbine fuel, is not a single chemical compound. It is a soup, a complex mixture of hundreds of different hydrocarbons, typically ranging from 8 to 16 carbon atoms per molecule. A typical drop of Jet A1 consists of 3 primary hydrocarbon classes, each serving a critical function in the engine. First, you have the paraffins, comprising about 55 to 65% of the fuel. These are linear or branched chains of carbon saturated with hydrogen. They provide the bulk of the chemical energy. Isoalkanes, which are branched chains, are particularly prized because they burn cleanly and have excellent low-temperature properties, preventing the fuel from freezing at 30,000 feet. Their high hydrogen-to-carbon ratio means they produce more heat per kilogram and less soot. Second, there are cycloalkanes, also known as naphthenes, which make up about 20 to 35%. These are rings of carbon atoms saturated with hydrogen, like cyclohexane or decalin. Their primary function is density. Jet fuel is sold by weight but stored by volume in wing tanks. High density means more energy can be packed into the limited space of an aircraft wing. Finally, and most controversially, we have the aromatics, specifically alkylbenzenes, making up about 8 to 25%. Structurally, these are planar rings with delocalized pi electrons. Historically, aromatics were considered impurities that were hard to remove, but they became essential for legacy aircraft seals. The nitrile rubber O-rings in older engines absorb aromatics and swell, creating a tight seal. Without them, seals can shrink and leak. However, aromatics are the primary precursor to soot. Upon combustion, their stable ring structures act as nucleation sites for particulate matter. These black carbon particles serve as seeds for ice crystals, forming persistent contrails that trap heat in the atmosphere. This is a non-CO2 warming effect that may be just as damaging as CO2 itself. The goal of SAF chemistry is to replicate the energy density and cold flow properties of paraffins and cycloalkanes while minimizing or eliminating the aromatics, all without breaking the seals of existing engines. Let us look at the first production pathway, the workhorse of the industry, known as HEFA, or hydroprocessed esters and fatty acids. As of 2026, HEFA accounts for over 80% of global SAF supply. It relies on lipid feedstocks like waste cooking oils, animal fats, and plant oils. The chemistry here transforms triglycerides, which are massive molecules with 3 long fatty acid chains attached to a glycerol backbone, into simple, high-quality paraffins. The first step is hydrodeoxygenation. The triglycerides are treated with hydrogen gas at high pressure, between 30 and 80 bar, and high temperatures up to 400 degrees Celsius. This happens over a catalyst, typically nickel molybdenum or cobalt molybdenum, supported on alumina. In this reaction, the glycerol backbone is severed and converted to propane. The oxygen atoms in the fatty acid chains are stripped away, reacting with hydrogen to form water. You are left with long straight-chain N-alkanes, essentially identical to renewable diesel. However, pure N-alkanes freeze at temperatures far too high for aviation. To fix this, we move to the second step, selective hydrocracking and isomerization. The chains must be cracked or shortened and isomerized or branched. This uses a platinum or palladium catalyst on a zeolite support, which is an acidic molecular sieve. The zeolite's acidic sites protonate the alkane chain, forming a carbocation. This unstable ion rearranges itself, branching out to form an isoalkane, or splits into shorter chains. By tuning the reaction severity, chemists can maximize the yield of kerosene range molecules. The final product is a synthetic paraffinic kerosene. It is crystal clear, sulfur-free, and aromatic-free. While it burns significantly cleaner than fossil jet fuel, reducing soot by over 50%, the lack of aromatics means its density is lower. requiring it to be blended with fossil fuel to ensure seal swelling. While HEFA relies on waste grease, the second pathway, alcohol-to-jet, unlocks the vast potential of carbohydrate feedstocks like corn, sugarcane, and cellulosic biomass. This pathway is a masterclass in oligomerization, building larger molecules from smaller blocks. It starts with dehydration. An alcohol like ethanol is passed over a solid acid catalyst, such as gamma alumina or ZSM-5 zeolite at elevated temperatures. Intramolecular dehydration occurs, removing the hydroxyl group and a hydrogen atom as water. Ethanol becomes ethylene, or isobutanol becomes isobutylene. The next step is the critical chain growth step called oligomerization. Since light olefins like ethylene are gases, they must be linked together to form liquid jet fuel. Using acidic resin catalysts like ZSM-5 or amberlist, a cationic polymerization occurs. An acid site protonates an olefin, creating a carbocation that attacks another olefin double bond. Carbon units link to form larger chains. By controlling temperature and pressure, chemists steer the distribution toward dimers, trimers, and tetramers, hitting the jet fuel sweet spot. Finally, via hydrogenation using nickel or palladium catalysts, the unstable double bonds are saturated with hydrogen to form stable isoalkanes. The result is a fuel that is chemically highly consistent. Unlike the fossil soup, alcohol-to-jet fuel can be engineered to be predominantly a single type of highly branched isoparaffin, offering exceptional energy density and thermal stability. Now we arrive at the third pathway, often considered the holy grail of e-fuels, Fischer-Tropsch and power-to-liquid. This requires no biological feedstock, only water, carbon dioxide, and renewable electricity. It mimics the geological processes that formed oil, but accelerates them from millions of years to minutes. It begins with electrolysis to split water into hydrogen and oxygen. Then, through the reverse water-gas shift reaction, stable CO2 is stripped of an oxygen atom to become reactive carbon monoxide. This endothermic reaction requires temperatures over 800 degrees Celsius and catalysts like copper or nickel on Syria supports. The resulting mixture of hydrogen and carbon monoxide is called syngas. The Fischer-Tropsch process then polymerizes this gas into liquid hydrocarbons. For aviation fuel, cobalt catalysts are preferred because they promote chain growth. The CO molecule adsorbs onto the cobalt surface and dissociates. Hydrogen atoms hydrogenate the surface carbon to form monomers, which migrate and link together, growing a chain one link at a time. The chain growth follows the Anderson-Schultz-Flory distribution, producing a mix of gases, naphtha, kerosene, diesel, and solid wax. The heavy waxes are then hydrocracked into the jet fuel range. The result is the cleanest fuel known to man. It has near-zero sulfur and aromatics, burning with a pale blue flame and producing negligible soot. But like HEFA, it lacks density. A rapidly growing alternative to Fischer-Tropsch is the fourth pathway, methanol-to-jet. Championed by major chemical conglomerates, this route turns syngas into liquid methanol first, which is easier to transport. The methanol is passed over a SAPO34 catalyst, a silico-aluminophosphate with cage-like pores. Inside these pores, a hydrocarbon pool mechanism occurs where trapped organic species act as a scaffold, reacting with methanol to eject light olefins. These olefins are then oligomerized using ZSM-5 zeolite. A key advantage here is that ZSM-5 can be tuned to allow cyclization reactions. Unlike Fischer-Tropsch, which makes only straight chains, the methanol-to-jet pathway can naturally produce cycloalkanes and aromatics. This means it could potentially create a fully formulated fuel that does not need blending with fossil jet fuel. This brings us to the missing piece of the puzzle, renewable aromatics. For a 100% SAF future, we must synthesize the aromatic function for the seals without the soot penalty. Chemical engineers are developing bioaromatics from lignocellulosic biomass. For example, the furfural pathway takes xylose from hemicellulose and dehydrates it to furfural. Through a Biancatelli rearrangement and subsequent condensation, two molecules combine and are hydrodeoxygenated to form fused bicyclic alkanes like decollin. These renewable cycloalkanes have densities greater than 800 kilograms per cubic meter, solving the density problem of other green fuels. Another method uses Diels-Alder cycloaddition, reacting furans with ethylene to form renewable benzene or toluene, chemically identical to fossil aromatics but made from wood. Finally, we must discuss the ultimate recycler, plasma gasification of municipal solid waste. This turns trash into jet fuel. Standard combustion burns waste, but plasma gasification dissociates it. An electric arc ionizes gas into plasma, reaching temperatures between 3,000 and 7,000 degrees Celsius. At these temperatures, organic matter does not burn. The molecular bonds shatter. Complex polymers break down into their atomic building blocks. As the mixture cools, these atoms recombine into hydrogen and carbon monoxide, forming syngas. Inorganic materials melt and drip to the bottom, cooling into an inert vitrified slag. The dirty syngas is scrubbed of chlorine and sulfur, then fed into a standard Fischer-Tropsch reactor. It is alchemy at an industrial scale. When we compare the physics of these fuels to fossil jet A1, the differences are stark. Fossil fuel is a mix of paraffins, naphthenies, and aromatics, with a density around 800 kilograms per cubic meter. Neat SAF produced via HEFA or Fischer-Tropsch is over 98% paraffinic, with a lower density around 750 kilograms per cubic meter. This means neat SAF has lower volumetric energy density, but superior energy density by mass, offering more range per kilogram of fuel payload. Most importantly, SAF creates significantly less soot and eliminates sulfur emissions. Currently, blending limits of 50% exist because of the seal swell and density requirements, but the future lies in synthetic aromatics or modified engines. By 2050, the skyline will look different. The chemistry of flight is transitioning from extraction to synthesis. HEFA is our bridge, cleaning up waste lipids. Alcohol-to-jet is the expander, mobilizing agricultural carbon. And power-to-liquid is the destination, closing the carbon loop with infinite feedstocks of air, water, and sunlight. By 2030, a boarding pass will represent a complex chemical backstory: hydrogen stripped from water, carbon captured from the air, and molecular chains stitched together by cobalt and zeolite. We are no longer just burning fuel, we are designing it.